So why is it that the buoyant force acting on a submerged object is equal to the weight of the displaced fluid? The weight of the displaced fluid. That is the question that we'd like to answer. And the way that Pascal approaches this is by considering the forces acting on each of the faces of a submerged object, and then demonstrating that the forces that act on the two sides, so if this is a submerged object, there are forces acting on the two sides of the object. Those two end up balancing each other, but the force acting on the bottom is larger than the force acting on the top, and so the net result is there's an overall upward force. So we have to find a way of finding out the force acting on the bottom and the force acting on the top, and then demonstrating that the total buoyant force, which is equal to the difference between the force acting on the bottom and the force acting on the top, so that's the buoyant force, is the difference between those two, somehow demonstrating that that buoyant force happens to be equal to the weight of that fluid displaced. So how do we demonstrate that? So that is what I'm going to do now. So I'm going to prove this. Proof. Okay, so the first thing we're going to do is notice that the pressure of the fluid, the pressure exerted by a fluid on a submerged object depends on the depth of the fluid. So as you get deeper in a fluid, the pressure at that point is larger. Why is it that the pressure gets greater as you go down? Well, essentially it is because there's more fluid above it weighing down. So let me draw a picture here. So if we have water or any other fluid for that matter, and we imagine some thin, very thin plate submerged in this fluid. So this is going to be at some depth h, and the density of the fluid is Greek letter rho, and let's suppose the area of this plate is A. Then what we really need to consider is the weight of this column of fluid above there, and that weight of that fluid is what's pushing down on the face of that. So the weight of the fluid in this region up here, the weight of that is equal to the mass of that fluid times g, the acceleration of gravity. And what is the mass? Well, that's the density of the fluid times the volume of fluid in that region. And what is the volume of the fluid in that region? Well, it's going to be equal to the area times the height. That is going to be the volume enclosed right there. So in other words, the weight of all this fluid above that plate is the density times the area times the height. That is the depth below water times g. And now what we can do is we can calculate the pressure at the depth h. We can call that pressure, which is a function of h, or the depth. That is going to be the weight of all that fluid divided by the area. Remember, pressure is a force over area, right? And the weight is a force, so it's weight over area. So we can take this W right here and plug it in. That's the weight of all that fluid above that area of the plate. And so the pressure at this depth h is just the density times the area times h times g over the area. Or we can write that the pressure at this depth h is equal to, well, the a's cancel out. It's the density times the depth times g. This formula is a very important formula. It tells us what the pressure is at any depth h in a fluid. This is called the hydrostatic pressure at that depth. That is the hydrostatic pressure at that depth. So anytime you have some object submerged in a fluid and it's at some particular depth h, we can find the pressure at that depth. Okay? Now, that's step one. Let's continue. So step two of our proof is that the pressure P of H pushes in all directions. Presses in all directions, not just down on the top. Not just down on the top, but also up on the bottom of a submerged object. So not just down on the top, but also up on the bottom of a submerged object. Okay, so if this is underwater, if we kind of go back to our original drawing right here, we imagine this object underwater, there is going to be, at this depth here, there's going to be some pressure at that depth, and we'll call the pressure that's acting on the top of the block. And then at a greater depth, there's going to be a different pressure, and that pressure is going to yield this force pushing up on the bottom. Okay, so this then would be step three in our proof, is to ask ourselves, what is the difference between the forces acting on the top and the bottom of our submerged object. And you might kind of see where we're going with this, because the top is below water at a certain depth. It has some pressure, which yields some force, and the bottom is deeper, and so the pressure is higher down there, and that leads to a bigger force. So there's a larger force on the bottom than the force on the top, and that's what's precisely going to give us this buoyant force right here. So what is the pressure acting on the top? Well, let me draw a picture. So let's draw some water here, and let's draw our submerged object. I'm going to draw it kind of in 3 dimensions here. Okay, so here is our object, and the top of it is at some depth ht, and the bottom of it is at a different depth hv. So maybe this is 1 meter under the water, and maybe this is 2 meters underwater. Those are the different depths. And so the height of this object, that's the height of this object, we can call that delta H, which is the height or the depth at the bottom minus the depth at the top. Okay. Okay. Now, what do we do from here? Well, we want to find the total buoyant force acting on this object. The total buoyant force is going to be equal to the force that's pushing up on the bottom minus the force that's pushing down on the top. That's what we said over here. The buoyant force, that's a net force, is equal to the difference between the forces on the bottom and the force on the top. Well, what is the force pushing up on the bottom of this object? Whoops. So the force that's pushing up on the bottom of this object, and we've got this force pushing down on the top of the object. Okay, what is that force pushing up on the bottom? Well, that would just be the pressure at the bottom, which is a force per unit area, times the area of the bottom of that object. And what's the force on the top? That's whatever the hydrostatic pressure is at the top times the area of the top, right? So this is the difference between the forces. Now we can factor out the area because we're assuming the area on the top and the bottom are the same. It's not necessarily always the case, but it makes it easier to calculate this. So factor out the area, pressure bottom minus pressure top, like this. Well, what is the pressure acting on the bottom? Well, the pressure, we already know what the hydrostatic pressure is at that depth. It's going to be equal to the density of the fluid times the depth at the bottom of this object times g. And what's the pressure acting on the top? Well, once again, that's a density times the depth at the top of the object times g. And you can see that rho and g are common to these two factors, so area times rho times g times the height bottom, or the depth on the bottom, and the depth at the top. And here we'll keep going, area times the density times g. Well, the difference hb minus ht, that's just the height of the object itself. That's delta h. That's what we said right over here. So why does that matter? Well, notice now I'm going to rearrange this a little bit. We'll have the density g and then area times delta h. Notice I've just moved this a over there. I put these together in a suggestive way. Well, what is the area times the height? That is just the volume of this cylindrical object. That's the volume of this object. Now, notice what we've done. We've said that the buoyant force is equal to the density times g times volume. Well, let me rearrange this one more time. Pull the g right here, and the density times the volume. This right here is the density not of the object, but the density of the fluid, right? So this quantity right here, rho v, is just the mass of the displaced fluid. In other words, what we've just demonstrated is that the buoyant force acting on this object, that is the upward force, is equal to the weight of the displaced fluid, which is exactly what Archimedes' principle says. Archimedes' principle says that the buoyant force acting on a submerged object is equal to the weight of the displaced fluid. And this is the insight that Pascal had. He recognized by thinking about how the hydrostatic pressure varies with depth, one can get a deeper and clearer understanding of why it would be that Archimedes' principle holds.